Video, we're going to go over rational functions. And there's a lot to do in this video. We're going to first talk about characteristics of it, finding domain, finding asymptotes, and then eventually moving into things such as holes or removable discontinuities, then some graphing using all the characteristics with the help of some technology like Desmos, and then ultimately finishing with giving you the graph and you having to write the actual function. All right, so a lot to do here. The key thing you need to know, we've talked about this since the very first unit in this class, is that rational functions you should see usually is a fraction, all right, and it has your variable in the denominator. So that's the key thing here you're looking for, is you're looking for that variable in the denominator, okay? Now, in terms of finding the domain, it's really just all about the denominator, okay? So let me do a couple examples, all right? So when I look at this first function, f of x, is x plus 3 over x squared minus 9. I notice in the denominator that that is the difference of two squares. So I'm going to go ahead and factor that. So copy the top. But my new denominator is going to be x minus 3 times x plus 3. All right, and so you should notice that we have the same factor on top as we do on the bottom. This is what creates a hole, or as we'll learn later, the technical name for this in calculus is a removable discontinuity. So it means that it's discontinuous at that value. So I always like to write this right away. A hole at x equals, and whatever would make that 0, which would be negative 3. Okay? Now, in a moment, we'll go ahead and find where that hole would be, and we'll do some more practice later. But for now, I just want to rewrite the function without that term that creates that hole. So here is that function. So when you get to this point, you'll notice we can't do any more crossing out. So we're going to write that there's a vertical asymptote. So VA stands for vertical asymptote at whatever makes your denominator 0. So in this case, I'm looking at x minus 3, and the value that would make the x minus 3 become 0 would be positive 3. All right. So we're going to have two issues in our domain. It's going to be when x is negative 3 and when x is positive 3, but two different things happen there. You notice in the sketch, right here is that hole, right? So that hole at negative 3, right? And then here is that vertical asymptote at positive 3. So both are discontinuities. You'll see in calculus that the vertical asymptote is called infinite discontinuity. And then, as I mentioned, this hole in calculus is named removable discontinuity. So in terms of our domain, you're not going to be able to decipher in the domain which one is which, but the sketch obviously will help you. So negative infinity to that hole at x equals negative 3, then negative 3 to that vertical asymptote at positive 3, and then 3 to infinity. So essentially, like we did in the first unit, we're saying that the domain is all real numbers, except for x cannot be equal to negative 3 or positive 3. But now you can see, officially what's going on at each of those x values. Let's do another one here. So this one is already fully factored, and we're not able to cross out anything. So when I look at this, I'm just thinking about my vertical asymptotes, or whatever makes my denominator equal to 0, which is a positive 1 and a positive 5. Okay, so when I do my domain, because I don't have any holes, it's just going to be about the vertical asymptotes. So negative infinity to positive 1, 1 to positive 5, right? That's my next vertical asymptote. And then 5 to positive infinity. You can look at the sketch too to see kind of what's happening. So I told you there's a vertical asymptote at x equals 1, a vertical asymptote at x equals 5, and as I said, we don't have any removable discontinuity. So that's the domain for this second one. All right. Now, in terms of identifying the vertical asymptotes, as I mentioned before, all right, we'll do another example here with this k of x. But all you want to do is make sure that everything is fully factored. And if you have already crossed out your common factors in the top and the bottom to create that hole, or if you don't have any common factors in the top and bottom, it's all about looking at the denominator. So when you're looking at finding vertical asymptotes, you need to be thinking about, look in the denominator. All right, so let's make sure we can fully factor this. So I'm going to rewrite it again, but I'm going to write down 2x squared plus 5 okay, all over. And then I'm going to rewrite this in order from least to greatest in terms of my exponents. Negative x squared minus x plus 2. Now I can't factor the top, right? The top doesn't have a common factor, and it's not the difference of two squares. So I'm going to just focus on the bottom, which again is what I care about anyway with this, the denominator. And so I'm going to factor out that negative first. That's right, the opposite of x squared plus x minus 2. You don't have to do that. I just find that students have way more success if you're factoring where your first term is a positive x squared. So keep that negative. Let's think of factors of negative 2 now that add to positive 1. So that's going to be positive 2 and negative 1, right? That's going to end up giving me that trinomial that's in the denominator. All right, so you'll notice I don't have any common factors in the top and the bottom, so no holes here. So my vertical asymptotes, which you can always use VA for vertical asymptotes, is going to be x equals that negative 2 and x equals a positive 1, right? You always want to think opposite when you're writing down your vertical asymptotes. So again, no holes, just vertical asymptotes. Now, I mentioned that in calculus, we don't call them holes anymore. We call them removable discontinuity. All right, so if you look at this example, they've already factored it. It's a common factor at x plus 1 in the top and the bottom. So that means we're going to have a hole at x equals negative 1. And then in terms of finding out, the y value for where they plotted it, right? They had to plot it somewhere. You're going to plug that x value of negative 1 into what's remaining. So you're going to plug it into negative 1 minus 1 over negative 1 minus 3. So that stuff didn't get crossed out. So I plug it into the x. Both two x's, actually two instances where it's remaining. So that's a negative 2 over negative 4, which is a positive 1/2. So you can see the y value they chose is positive 1/2 for that hole. All right, anyway, that's just kind of a review again. Hopefully something you've seen before in your Algebra 2 class. You'll notice again, there is that vertical asymptote at x equals 3, right? That's from this denominator. And we'll talk later on in this class that whatever makes your numerator 0, in this case 1 minus 1 would be 0, gives you your x-intercept. Okay. So we've got removable discontinuities, all right, when you look at this. And it wants us to essentially, with these two questions, do a bunch of factoring to then determine what's going to give us a removable discontinuity and then what's going to give us the vertical asymptotes. So I'm going to go ahead and factor this to be k of x equals x minus 2 over, this is dots, x minus 2 and x plus 2. All right, so we have a common factor in the top and the bottom, this x minus 2. So I now have a hole at x equals positive 2. Remember, I always want to think opposite. Now, to find that y value, I'm going to plug my value of 2 into what's remaining. And what's remaining is 1 over x plus 2. So I'm going to do 1 over 2 plus 2, which is 1/4. So my hole is going to be at positive 2, comma, 1/4. Now, in terms of my vertical asymptotes, right, you can notice that my function, once the holes are gone, is really not a whole lot here, right? It's just 1 over x plus 2. So whatever makes that denominator 0, all right, whatever makes that denominator 0 is going to give me my vertical asymptotes. That's x equals negative 2. So there's one vertical asymptote and one removable discontinuity. Let's try this next one. All right, so a lot more factoring to do here. I'll go ahead and factor the top, which is the difference of two squares. So x minus 5 times x plus 5 all over. I'm going to factor out this x first, which gives me x squared minus 6x plus 5. All right, keep going. So I'm going to have the top stay the same, which is x minus 5 times x plus 5 all over, copy down this x. So now if I factor that trinomial in the bottom, I get factors of 5 that add to negative 6. That's negative 1 and negative 5. Okay? So when you multiply those, you get positive 5. When you add them, you get negative 6. And you can see we have a common factor in the top and the bottom. So x minus 5 and x minus 5. So we have a hole. So I'm going to start writing it. a whole at x equals whatever, think opposite there, so whatever makes that 0 is positive 5. All right, so I'm going to plug that into what's remaining, okay, and here is what's remaining. It's just x plus 5 over x times x minus 1. And if it helps your brain to put that in parentheses as well, that's fine. Don't start crossing out stuff. You can only cross out if the factors are the same. So they need to be in parentheses with multiplication, and then obviously one on top and one on the bottom. So let's plug in 5 into what's left. So 5 plus 5 all over 5 times 5 minus 1. So that's going to be 10 over, let's see, 5 minus 1 is 4. 4 times 5 is 20, which is 1/2. So my whole, all right, I'll put it right here. My whole is 5 comma 1/2. Now, in terms of my vertical asymptotes, if I'm looking at the remaining function, right, this right here is my remaining function once the whole has been accounted for. And if you look at the denominator, we have x cannot be equal to 0, right? That's that lone factor of x. And also x cannot be equal to positive 1. All right, so that's my other vertical asymptote. So that's all the asymptotes and the removable discontinuity for this other one. Okay, let's talk a little bit about how to find horizontal asymptotes. Now, this is going to be like, there's a lot more here than you really need to, and I'll definitely try to prep you guys for what you'll need to know for the test. But the key thing is that there's really 3 different ways that you're going to identify a horizontal asymptote. It always has to do with the degree of the numerator and the degree of the denominator. When I say degree, right, we practiced in class a few weeks ago, is that once you have it written in order from the highest exponent to the lowest exponent, your degree is always your first exponent you see. And if it's not written in order, you need to find the highest exponent. All right, so in this case, if I look at this example, this is x to the first power and x to the second power. So the degree in the numerator is 1, and the degree in the denominator is 2. So in this instance, when the degree of your numerator is actually less than the degree of your denominator, which I know in the case 1 up here, if you're reading it, they have it switched. I always say it in that order, but it doesn't matter. As long as you know that if the degree of your numerator is less than the degree of your denominator, your horizontal asymptote, so I'm going to do HA for horizontal asymptote, will always be y equals 0. So in this case, you can see in this sketch, the horizontal asymptote is y equals 0, that kind of turquoise horizontal line. Now, you can look at the vertical asymptotes if you want, right? We just spent 10 minutes practicing that. That's when you would factor the denominator, see what makes it 0. It gives you those 2 vertical asymptotes. But in this case, we're just looking at finding the horizontal asymptotes. This is what I call case 1. Degree of the numerator is less than the degree of the denominator. That's always the case. Then it's y equals 0. Okay, let's give you another example. All right, now what if, this is actually not the way order I would do it, but that's fine. Now, what if the degree of your numerator, so in this case, let's do the degrees again. So in this case, the degree is 2 for that x squared, and the degree in the denominator is 1 for x to the first power. You'll notice now the degree of the numerator is greater than the degree of the denominator. So if this is the case, what we say is we have no horizontal asymptote. Okay, I'll repeat that again, all right, if you're listening. All right, if the degree of your numerator is greater than the degree of the denominator, then there's no horizontal asymptote. All right, if the degree of the numerator is exactly 1 more than the degree of the denominator, which in this case we have a degree of 2, degree of 1, 2 is greater than 1 by exactly 1, then what we have is called a slant asymptote. So this won't always be the case. All right, so I'll repeat that. If the degree of your numerator is greater than the degree of the denominator by exactly 1, then you do have what is called a slant asymptote. So in this case, we do have a slant asymptote. The way you find this is to do division. Now, if you're able to do synthetic division, like in this case, when you look at the denominator, it's in that form x minus a, which you practiced a few lessons ago. I am going to use synthetic division. If it's not in that form x minus a in the denominator, you will use long division, all right? But I'm going to try to be nice, and if there is a slant asymptote, I'll try to make sure it is okay to use synthetic division. So 3, -2, and +1. So bring down the 3. 3 times 1 is 3. When you add this together, you get 1. 1 times 1 is 1. And so when you do this for slant asymptotes, so notice I'm trying to find the slant asymptote. I actually don't care what the remainder is. So your slant asymptote, or SA, is going to be y equals 3x plus 1. You'll notice I'm not writing the remainder, just using those first two numbers to write the slant asymptote. There it is sketched. And your slant asymptote will always be a line with slope that's not 0. I'll repeat that. Your slant asymptote will always be a line that has a slope that is not 0. Okay, that's why it's called slanted. Okay, let's do the last case, which is really, in my mind, the second case. What happens if the degrees are the same? So in this case, your degree of the top is 2, and your degree on the bottom is also 2. Okay, so if they're the same, then you do have a horizontal asymptote. Right, so you do have one, and it's equal to the leading coefficient of the top. Let me write it like this. Y equals the leading coefficient from the numerator over the leading coefficient from the denominator. So the leading coefficient at the top is 3. The leading coefficient in the denominator is 1, right here, 1x squared. So your horizontal asymptote is y equals 3, which you can see graphed right here. Okay? Now, when you sketch these, and even if you're looking at this example sketch, you can see that you are crossing that horizontal asymptote, and even in the slant asymptote, it didn't happen there, but it can in certain cases. You're going to see in these sketches that not all the curves are going to follow all the rules. You should know your vertical asymptotes. It will follow the vertical asymptotes pretty much to a T every time, but your horizontal asymptotes and your slant asymptotes might get crossed every once in a while. So it's one of those things where it's okay when you're sketching with Desmos to be like, wait, why is it crossing like that? It's all right. Just use that technology to help you solidify what it looks like. Okay, so let's kind of use all that to help us find horizontal and slant asymptotes. So a little practice, and then we'll go ahead and start graphing, which is kind of the whole point of this, okay? So letter A, all right, I noticed that the degree in the top is 3, and the degree in the bottom is also 3. So my horizontal asymptote is going to be y equals the leading coefficient from the top, which is 6, over the leading coefficient from the bottom, which is 2. So my horizontal asymptote is y equals 3. All right, look at letter B. Letter B has a degree in the top of 2 over the degree in the bottom, which is 1 x to the first power. So this has no horizontal asymptote, all right? And so it has no horizontal asymptote because the degree of the numerator is greater than the degree of the denominator, but it does have a slant asymptote because that degree difference is exactly 1. So I'm going to do a little work here for letter B. I'm going to put -2 in the corner. All right, think opposite. 1, -4, and 1. Bring down the 1, multiply by the number in the corner. Add. Repeat the process. Again, I don't care about the remainder. So your slant asymptote is going to be y equals x minus 6. So y equals x minus 6. All right, and the last one has a degree of 2 in the top, and in the bottom, it's a degree of 3. So if the degree of the numerator is less than the degree of the denominator, you do have a horizontal asymptote, and it's going to be y equals 0. All right, so again, just some practice with those cases and having to do some math, some synthetic division for the slant asymptote. Okay, now let's get into finding intercepts, which is really our last characteristic that we need to do, and then we will be ready to graph. So in terms of the y-intercept, this one is true for any function. You're just going to plug in 0 for x. So I'll do 0 minus 2 times 0 plus 3 all over. 0 minus 1, 0 plus 2, and 0 minus 5. So you get -2 times 3, which is -6. That's -1 times 2, which is -2. -2 times -5 is a positive 10. So you get -3/5. So your y-intercept, when you plugged in 0, you got -3/5. Okay? Now in terms of the x-intercepts, when you do the x-intercepts, if it's already factored for you like this, it's actually pretty straightforward. The x-intercepts, as I mentioned earlier, you look in the numerator. Whatever makes your numerator 0, that's going to be your x-intercepts. The reason for this is because you're trying to make the entire function become 0, right? So if you want to set it up, I never do this, but let me just show you kind of what I'm talking about. If you write, just copy it again. All right, so there it is, copied down my function. And then if you set it equal to 0, right, if you think of this as like equal to 0 over 1, if you use cross products like it's proportion, your entire denominator is going to multiply by 0. So really what ends up happening is that your numerator ends up being equal to 0. So whatever is going to make this become 0 gives you your x-intercept. So in this case, thinking opposite, you get 2, 0, and negative 3, 0. So that's always the case for any rational function. To find the x-intercepts, just figure out what makes the numerator become 0. Okay, now let's do all that stuff to help us sketch a graph, and then we'll use some technology to finish it. So you can go in any order you want. It doesn't matter. I'm going to start with the vertical asymptotes. That's kind of the first thing we did. I don't see any common factors in the top and in the bottom. Right, so I can't cross anything out to have any holes. So in terms of my vertical asymptotes, whatever makes my denominator 0 is x equals -1 and x equals +2. In terms of my horizontal asymptotes, all right, my degree of my numerator is 2. X times x is x squared. My degree of my denominator would be x squared times x, which is x cubed. If the degree of the numerator is less than the degree of the denominator, then it's y equals 0. Let's find the y-intercept. Go and plug in 0 for our function, so f of 0. All right, so we get 2 times -3, which is -6. 0 plus 1 is 1 squared is 1. 1 times -2 is -2, so you get 3. So your y-intercept is 0, 3. Again, finding those x-intercepts, if they give it to you like this where it's fully factored, it's pretty straightforward. Whatever makes your numerator 0, which is -2, 0, and +3, 0. All right, so at this point, I'm going to go in and start putting these characteristics on the graph. So we have a vertical asymptote at x equals -1. Another one at x equals 2. And then we have a horizontal asymptote at y equals 0, which is the x-axis. Plotting my y-intercept of 0, 3, then -2, 0, and 3, 0 for the x-intercepts. That's it in terms of what I know from my characteristics. So now I turn to my technology, type this into Desmos, and see how to finish the sketch. All right, so I have x plus 2 times x minus 3. Over x plus 1 squared times x minus 2. Okay, so you'll notice we have our vertical asymptotes. And you don't have to do this, I'm just showing you that this is what we have for our vertical asymptotes at x equals 2. All right, so you can see those there. All right, and it looks like we have our y-intercept at 0, 3, x-intercepts that we plotted already. So I'm going to go ahead and finish this sketch based on the technology. And remember, you will have access to this when you're working on these questions in class. So this one on the left, all right, is going to come down and go through it, and then kind of come back towards that asymptote. In the middle, we've got kind of almost looks like a parabola a little bit. All right, and then finally on the right side, we've got our curve going like this. And again, on my test, on my stuff, I really just put kind of a blank x and y axis so you can do your sketching, because that was kind of tight for that middle parabola, okay? Let's do one more, and then we'll do a last problem of kind of going the other way, where I give you the graph, and you've got to find what the function is based on the characteristics. All right, so we have vertical asymptote. Looks like nothing's crossing out. So vertical asymptote, what makes the denominator 0? +1 and +3. All right, horizontal asymptote. Let's see if we can do this one here. So horizontal asymptote, the degree of the numerator is going to be x cubed, right? X squared times x is x cubed. The degree of the denominator is x squared times x, also x cubed. So it's going to be y equals the leading coefficient from the top, which is 1, over the leading coefficient from the bottom, which is 2. So y equals 1/2. All right, let's find the y-intercept by plugging in 0. So f of 0. So it'll be 0 plus 2 squared times 0 minus 2 all over. 2 times 0 minus 1 squared times 0 minus 3. All right, so that's going to be 4 times -2, which is -8. -1 squared is 1. 1 times -3 is -3 times 2 is -6. So reduced to a +4/3. And the x-intercepts, since it's already factored, whatever makes the numerator 0, I've got -2, 0.
Teacher.
And then I've got +2, 0. All right, now, one thing I do notice is when you're looking at this x plus 2 is raised to the second power. So this root, right, that makes it 0 is what we call a double root. And you'll see when we sketch it that when we touch the x-axis there, we're not going to cross it. All right, we're going to touch and turn back. All right, so let's put down our vertical asymptotes. X equals 1. And then x equals 3. All right, we have a horizontal asymptote at y equals 1/2. Okay, our y-intercept is 0, 4/3, so 0 and 1 1/3. X-intercepts at -2, 0 and +2, 0. All right, so that's all I got. Let me go ahead and type this into our graphing calculator so we can see what the rest of it looks like. Okay, so x plus 2 squared times x minus 2. And then 2 times x minus 1 squared, x minus 1 squared times x minus 3. Excellent. So as I did before, again, you don't have to do this. My vertical asymptotes, x equals 1, x equals 3. All right, so you can see those there. All right, and again, I mentioned we have that double root at -2, 0, so you can see we're touching it, but we're not actually crossing the x-axis, and this one does actually cross, and there's our y-intercept. All right, so we can make the rest of our sketch here. We're going to have this curve coming down. Try that again. And then, again, don't cross it. Something like this. And then this one, it looks like it's kind of going from the top left to the bottom right here. And then finally, this one on the right, I have no points to plot, just got to make my curve and kind of follow the asymptotes. All right, and again, I'm not that concerned. Just do your best on the sketch. All right, we finally made it to our last one. This is a lot going on in this instructions, but what I just want you to see is I use the graph, right? So I look at the vertical asymptotes. That's going to essentially give me my factors for the denominator. And then I'm going to look at my x-intercepts, and that's going to give me my factors for the numerator. I'm going to put a letter A. They wrote it out here in front. I'm going to put it in the numerator, but you can put it out front. It's fine. It's your choice. I'm going to put it in the numerator. I'm going to solve for A using a point that they give me on the actual graph. So most likely, most of the problems that I do are going to give you the y-intercept. Okay, so let's kind of write down the stuff that's given to us here. So I'm going to do the vertical asymptotes first. So here's one vertical asymptote. here's another vertical asymptote. So my vertical asymptotes are going to be x equals a -1 and x equals a +2. Okay? Now, in terms of my x-intercepts, right, because this is going to give me my numerator stuff, I have -2, 0, and it doesn't look like a double root, it just looks like it crosses. And I also have +3, 0, and again, that looks like a single root. All right, because it looks like it's just crossing, okay? So now, here's what I'm going to do. I'm going to use that to write my function. Told you I'm going to do a letter A in the top. Now, my roots, my x-intercepts are going to give me my factors in the top, so think opposite here. X + 2 and x - 3. Do the same thing for the vertical asymptotes in the denominator. X + 1 and x - 2. Now, here's the thing that would probably be the difference between you getting it right and wrong on the test. It's kind of tough to see, but the horizontal asymptote is y = 0. So I'll kind of just put this as a little aside. So the horizontal asymptote is y = 0. And when we talked about this earlier in the lesson, if you have a horizontal asymptote of y = 0, that means the degree of your numerator needs to be less than the degree of your denominator. And right now they're the same, right? In the top you have x times x, which is x squared. In the bottom you have x times x, which is x squared. So in the denominator, we actually are going to have one of those factors is going to be raised to the second power. And it comes down to the fact that this piece, right, is moving kind of with that asymptote of x = 2. And same with this piece is also moving down towards -infinity on that asymptote. So because the end behavior for both of those is kind of using that same vertical asymptote, what that means is that this vertical asymptote x = 2, when you wrote that factor, it needs to be squared. And that would kind of check the box for having a horizontal asymptote at y = 0 now. So just, one of those things that's it's very small, but it could be the difference between you getting the correct answer or getting, partial credit. All right, so now I'm going to use the fact that my y-intercept is 0, -2 right there. So 0, -2. I'm going to make the f of x equal to -2 and plug in 0 for x to help me solve for a. All right, so I'm going to write down -2 equals a, and this is going to be times 0 + 2, which is 2. 2 times -3 is -6. 0 + 1 is 1. -2 squared. -2 squared is +4. 4 times 1 is 4. So if I want to get this a by itself, I'm going to multiply both sides by the reciprocal. So -4/6 times -4/6. So my a is going to be positive. All right, and so my a is going to be, let's see, that's positive 8/6, which is 4/3. Now, when you write this as the answer, you could write 4/3 out front, but what I like to do is because it's a fraction and my rational function is a fraction, is I'm actually just going to write the 4 on top and the 3 on the bottom. But it's your choice. Go back to before you found a, you had x + 2 on the top, x - 3 on the top, and then you have x + 1 times x - 2, all of that squared. All right, so this ends up being the answer for this particular rational function. I know that was a lot, right? These are 2 long videos. This is the longest lesson of the whole unit. But you're going to see that it takes a lot of practice, but you can find all these characteristics and use that to either sketch your own graph of it with technology or use the given graph to write a rational function for it. All right, make sure to practice. Good luck.